Welcome to Lecture 14, Section 3.1 of the text Elements of Modern Algebra by Gilbert and Gilbert. This is Dr. Gilbert, Eyabi. Section 3.1, Definition of a Group. Subsection 3.1.1, Definition. Let star be the binary operation defined for the elements of a set G. We say that G is a group if the following conditions hold. Number one, G is closed under the operation star, i.e., for every two elements x, y in G, x star y is an element in G. Condition 2. The binary operation star is associative, i.e., for every x, y, z in the set G, x star y in parentheses star z equals x star y star z in parentheses. If this equation holds, we say that the binary operation is associative. Condition 3. G has an identity element E, i.e., there exists an element E in G such that for every element X in G, X star E equals X and E star X equals X. Condition 4. G contains inverses, i.e., for every element X in G, there exists an element B that is also from G, such that X star B is E and B star X is E. If that is the case, we say that the inverse of X is B. Observe that commutativity is not in the definition of a group. Groups that are commutative have a very special name, and we shall come to that later. Example, determine whether the set of integers z is a group with respect to the binary operation star, where star is defined as x star y equals x plus y plus 1 for every xy in z. We're going to go ahead and verify the four conditions stated above. Condition 1, closure. We have to verify that for every xy in z, x star y would be in z. For every xy in z, x plus y plus 1 is also an integer because the sum of integers is an integer. Therefore, x star y, which is actually x plus y plus 1, is in z. In other words, for every xy in z, x star y is also an element in z. So we say that z under the operation star is closed. Condition 1, verified. Condition 2, we want to verify associativity. Let x, y, z be elements in z, the set of integers. Left hand side, x star y star z is the same as x star y star z by the definition of the binary operation star is y plus z plus 1. I consider all of these as one term, consider all of these as one term, and x star, this term y plus z plus 1 by the definition of star would be x plus y plus z plus 1 plus 1. And we are dealing with integers, so there is additive associativity, and that opens up to x plus y plus z plus 2. We call that equation 1. We now verify x star y star z. X star y star z. We start with x star y. That gives us x plus y plus 1 star z. All of this is a component. All of this is one component. And this component star z gives us x plus y plus 1 plus z plus 1 by the definition of our binary operation star. And again, we are dealing with integers here, so there is associativity in addition. So this equals x plus y plus z plus 2, and we call this equation 2. Equation 1 equals equation 2. So that means x star y star z equals x star y star z. So we just verified that the set of integers under the operation star is associative. Condition 2 holds. Now condition 3. In condition 3, we are required to find an element E such that for every element x in G, x star E equals x, and E star x equals x. So let's go ahead and find that element. Again, we want to find E in Z such that x star E equals x and E star x equals x. From equation 1, x star E equals x if and only if. Remember, we are not assuming the existence of E yet. We're simply saying that such an E would exist and would satisfy x star E equals x if and only if. That is the procedure we use to find a candidate for E. So x star E equals x if and only if x plus E plus 1, the definition of the binary operation star, equals x. Solving for E, that gives us E plus 1 equals 0, and that happens if and only if E equals negative 1. So E equals negative 1 is simply a candidate for the identity. To confirm that indeed E equals negative 1 is the identity, we have to check that if E here in equation 2 is substituted by negative 1, I would get negative 1 star x equals x. If that happens, then the negative 1 that we got would be confirmed as the identity. So substitute E equals negative 1 on the left-hand side of equation 2 and see if you get the right-hand side. E star x equals negative 1. That's the E that we have up here. Star x, and by the definition of our binary operation, that is negative 1 plus x plus 1, which equals x. Yes, we just verified that indeed negative 1 star x equals x. So we can conclude that E equals negative 1, which of course is an integer, is actually our identity element. 3 conditions down, 1 to go. Condition 4, inverses. Let A be an integer. Find an integer B such that B is the inverse of A, i.e., find an integer B such that A star B equals E and B star A equals E. Equation 1, equation 2. Just as we did with the identity element, we are going to use equation 1 to find a candidate for the inverse of A. Now, from equation 1, A star B equals E if and only if, again by the definition of the binary operation star, A star B gives us A plus B plus 1, E is negative 1, so we have A plus B plus 1 equals negative 1. Solving for B, that gives us negative A minus 2. To confirm that indeed B is the inverse of A under the operation star, we have to verify that number 1, B is an element in Z, and number 2, equation 2 holds. Clearly, A is an integer, B is an integer, negative A minus 2 is an integer, so B is an integer. We now have to verify that B star A actually equals E. So substitute B equals negative A minus 2 on the right hand side of equation 2, and we have B star A equals negative A minus 2 star A. By the definition of our binary operation star, that equals negative A minus 2 plus A plus 1, and that gives us negative 1, which is E. Therefore, we can conclude that for every integer A, there exists an integer B defined by negative A minus 2, and that integer is actually the inverse of A. Conditions 1, 2, 3, and 4 hold. Therefore, we can conclude that the set of integers under the binary operation star defined above is a group. So that is how we verify that a given set G is a group under a given binary operation star. I did mention above that commutativity is not one of the conditions that must hold for a given set to be a group. But there are several groups that are commutative, and these groups have a very special name. Let G be a group with respect to the binary operation star. Then G is called a commutative group or an abelian group if star is commutative. In other words, if G is commutative under the operation star, then we call G an abelian group. So we say that G under the binary operation star is an abelian group if for every x, y in G, x star y equals y star x. Example 1. This is a new group I'm introducing, and we shall talk more about this group as we move on in our studies of groups. It is called the Quaternion Group, G8. It has 8 elements, plus minus 1, plus minus I, plus minus j, plus minus k. The Quaternion Group is defined as follows. Negative 1 squared is 1. I squared equals j squared equals k squared equals negative 1. I times j is k. J times k is I. K times I is j. And ij is negative ji. Jk is negative kj. And ki is negative ik. You can see that commutativity doesn't hold. Ij is not the same as ji. It's actually negative ji. We shall talk a little bit more about this group in class. It's a very important group in the study of abstract algebra. So the Quaternion group is not abelian. Example 2. Let G be the set of all matrices in M3R. That means the set of all 3 by 3 matrices where the entries are real numbers. And this is the form. ABC is in R. Prove or disprove that G is a group with respect to multiplication. If it is a group, is it abelian? Solution. The first thing you want to do is to define G a little bit more rigorously. So we define G as the set of all 3 by 3 matrices where the entries A, B, C are real numbers. Verify the 4 properties of a group and also verify commutativity. If it is not commutative, give a counterexample. And of course, our operation star here is multiplication. I will leave that as a simple exercise for serious students. Subsection 3.1.3 definition. If a group G has a finite number of elements, then we say that G is a finite group, or G is a group of finite order. And we use the symbol OG to represent the order of G, which is the number of elements in G, or we use the absolute value of G to also mean the order of G, or the number of elements in G. If G does not have a finite number of elements, then G is called an infinite group. For example, the Quaternion group, which I introduced before, G8, has 8 elements. G8 is a group under the operation multiplication. And I want you to verify that. We will do it again in class, but you take some time and verify that indeed G8 as defined above is a group, but not an abelian group, and it is a finite group with 8 elements. The set of integers under the binary operation addition is a group, and it has infinitely many elements, so it is an infinite group. And talking about notation, since G8 has 8 elements, we say the order of G8, or the absolute value of G8, is 8. That means G is a finite group with 8 elements. This is just section 3.1 that deals just with the definition of a group. I'll see you in section 3.2, where we start looking at some properties of group elements. Thank you, and God bless you.